how hard is it to rewrite the foundations of physics? It's in an essay that you wrote a few years ago, you said that in some ways our project represents a radical shift from the past century or so of physics. You just alluded to that as well. And more often than not, when such intellectual shifts are made in the history of science, they've been accompanied by all kinds of difficulties in connecting with existing communities. Physics is arguably in its 7th generation, or maybe even the 6th generation, compared to other branches of science, which are much relatively newer. Physics is an old branch of science. It can be viewed as very firmly rooted, very static, intractable. For someone who comes across and tries to rewrite the foundations of the assumptions, I would imagine it's possible that self-doubt might creep in, that if this was the answer, someone else would have discovered it, or there's something down the line that's going to prove and everything, or disprove this and everything's going to fall apart. There's no roadmap for developing the fundamental theory. You're one of the few people who's actually working on this toughest question of our times. What are some of the unique challenges that you face in just taking up this quest?
Well, I think it's always the case. You have to believe that it's possible.
Yeah.
I mean, I think it's and this question, this thing, if it was possible, somebody would have done it before. Yeah. You know, I have to say one of the things that's been fortunate in my life is that I've done enough things that haven't been done by other people before.
Yeah.
That I kind of get the sense of what can be done and what cannot be done. Right. And I kind of believe in doing my homework. Like, you know, I know traditional physics really pretty well. So I kind of know what doors have been opened there, what things have been looked at. I know many of the people who worked on these things over the course of the last 50 years or so. And so, you know, I have some reasonable sense of what has been done, what has not been done. I mean, you know, when you look at some new field, it's always interesting when you enter some new field, and I've done this a bunch of times, there's a certain, you know, every field has its own intuition, its own kind of set of ways of thinking about things. And sometimes those ways of thinking about things are really good for the field. Sometimes those ways of thinking about things have kind of led the field astray. But it's always different for every field. So, for example, I've recently been doing some work in biology, which is a field where, for example, in physics, if there is a simple explanation for something, it's probably right.
All comes straight
in biology, the traditional experience is everything is more complicated than you can possibly imagine, right? There's always, you know, you say, oh, the genetic code works this way, footnote. Well, it has this little exception, footnote. It has this exception to the exception, et cetera, et cetera, et cetera. So it's that's a difference in intuition. So similarly, you know, I've been thinking a bit about economics. Again, a field with very different intuition and very different. Now, sometimes the intuition is important in understanding, it's certainly important in connecting to what has been done before. But, you know, I think the first step in doing something which has not been done before, it's really convenient to have done other things that haven't been done before because it builds up. I mean, you know, over the course of my life, you know, you have to have the confidence to believe that certain kinds of things you might imagine doing are possible. And as somebody, you know, leading a tech company for the last 37 years or something, that's one of the main roles that I have as CEO is, you know, projecting this confidence that the things I'm imagining doing are actually possible. Yeah. And, you know, that's a thing where I've been fortunate that essentially every big thing that I've imagined doing has turned out to be possible. Yeah. Now, it's, you know, I think there are things which I think about doing, which I don't know whether they're possible yet. And I don't think I'll really start seriously doing them until I get the sense that they're possible. Now, in terms of the fundamental theory of physics, that one, by the time I got serious about doing that by late 2019, I was sure that something was possible. I thought that the technical details and difficulties would stretch on for decades. Yeah. I didn't think that the things that sort of big things would fall out quickly. So that was that's an unusual, nice conclusion, because usually, you know, many kinds of projects one does, they have more tentacles, more difficulties than you expect at the beginning. And in fact, you know, particularly in technology development, one of the things I learned long ago is if you start off telling people this is really difficult and there are going to be all these complications and it's going to take 10 years to do this, it's really hard to get even yourself to be motivated to do it. I mean, I think I always have this point of view that I can do this and I don't know exactly how long it's going to take. And it's kind of like, oh, it might take a year or two. Well, maybe it takes 10 years. And then it's a matter of raw tenacity to actually get through the project. And that's a thing that has been, that's a challenging thing. And that's something where the fact that one has done other projects before that have worked out, I think helps fuel that tenacity, because it's kind of like, look, it's, this will get done, so to speak. Yeah. I mean, a thing that's happened to me recently is I just keep on doing these projects that are kind of finishing off things that I started. Well, the most extreme example was something I started 50 years ago, which I finally kind of got finished in the last year or so. In fact, I just did something in the last few days that was a thing that was kind of a leftover from about 42 years ago. There's a certain satisfaction in getting these things done. Yeah. It's also an encouragement, because those are things that I thought of doing a long time ago, and by golly, they were actually worth doing. In other words, it wasn't the case that I imagined things that one might do, and it's like, well, that wasn't a very good idea, I'm glad I didn't do it, type thing. So, but it's I mean, this whole question about what does it take, for example, in the fundamental theory of physics, you really have to kind of know existing physics. Yeah. That's an important, prerequisite. Another thing is just the technical tools that have been needed to actually make progress. Well, it so happened that I built a bunch of these tools. Yeah. So that's a convenient sort of, I didn't build them for this purpose, but I built them, and I don't think I'm the best. I'm not the best person at writing Wolfram language code, which I consider to be an achievement in a sense, but I'm pretty good. So, that allows me to take kind of ideas that I have and very quickly find out, sort of work out their consequences. And that's an important thing. The other thing that helps is that, I have an organization that I built that's quite substantial in size and has lots of, very talented people. Yeah. And so it's easy for me to get help in doing things. That's another sort of convenient feature, so to speak. Then it's, in terms of how do you, here's an issue that comes up, which is, there might be 100,000 papers about fundamental physics, things that somehow relate to what I'm interested in. I haven't read most of them. And you have to know enough that you can make use of what has been studied, and you can see whether you know what you're talking about and so on. But if you follow every detail of every one of those things, you will be drowning in sort of what is already known. And it becomes actually more difficult to figure out new things if you drown in what's already known. Because in fact, one of the mistakes that I saw myself making when I was much, much younger was kind of there's a conventional wisdom about something, and you know it, and you kind of assume, yeah, that's the way it must work. Mm-hmm. And it's like, well, no. And one of the antidotes to that, I mean, I remember actually there was an incident happened when I was like 17 years old. I was working on some physics problem, and there was a particular thing I needed to know about how certain particle interactions happen, and I kind of knew the conventional wisdom about this, which didn't really answer the question, and so on. And I'm like, I don't know what to do here. And then I realized I just wrote a paper that is specifically about this question, and I have an answer to this. And why on earth am I not using what I already figured out? And this is a thing that you see actually in the history of science a lot, that living in the paradigm you have built is actually a non-trivial thing, that people have a habit. The first generation of people who build a paradigm are always like, oh, this thing is built on sand, I'm going to have to go look elsewhere. So it is an active thing that you have to do to think, can the paradigm that I've built apply to the questions that I'm trying to answer? Or is it something where, and it's kind of like your own paradigm first and see if that works. If it doesn't, then you have to look elsewhere. But rather often my experience, particularly in recent times, has been, my gosh, I can actually say something about this. So that's the thing. I think this whole question of sort of how do you connect with things that have already been done, and it's kind of the thing that's been very fortunate about our physics project is that it sort of provides a machine code that seems to plug into a lot of things that people have put a lot of effort into. Yep. And, you mentioned physics being, I don't know how you compute the 7th generation, but that's an interesting number. It's certainly, physics is a field that has had many iterations and many layers of work done on it. And I think that, it's probably the most developed of the sciences. Mathematics maybe is a more developed thing in terms of the sort of towers that have been built.
Sure.
But physics is very developed. And that means, in a sense, that's good if you're trying to figure out what are foundations of it. But it provides kind of and it gives you, if you can find the foundations of what's there and you can see that those foundations are shared by, let's say, biology or economics or distributed computing, then the very fact that physics has made so much progress is really useful, because it means you can transport that progress that's been made in physics to other things that share the foundations, and you can make great progress in those areas as well. So that's been that's been an exciting thing to see. But in terms of, why is it hard to do fundamental theory of physics? The first thing is you have to have the confidence to think that, you can actually make progress. The second thing is you have to have a whole bunch of technical knowledge, without which you're just spinning, meaningless stuff, basically. And you also have to have a kind of good command of tools that are actually needed to make, to investigate things. And then maybe there's an element of, I don't know if it's luck or something else, which is kind of, I have a certain way of thinking about things that is very much oriented towards kind of simple structures and computation and following kind of computational rules and things like this. And, one might be lucky or unlucky in whether that paradigm is actually a hit for the way that certain things actually work. I think what seems to be the case is that I've been incredibly lucky in that paradigm really is a great way to think about these kinds of things. It may not be the only paradigm for thinking about these things, but it may be the one that, gets you one of the issues is, in a sense, nature does what nature does, but we are trying to understand what nature is doing. And we kind of have to make this bridge between what we understand and what nature is actually doing. And there may be different bridges that can be made, particularly if you have different foundational understandings for yourself. For me, this kind of computational understanding is one that happens to come naturally to me. And the fact that that bridge seems to be a makeable bridge is an exciting thing. And in some sense is kind of, one might think of it as luck, so to speak, because it might be that the easiest bridge comes from thinking about things in a quite different way that doesn't happen to be natural to me. And, I think one of the things that, for somebody like me, I'm a person who's watched a lot of other people develop, so to speak, and have been, I hope, I've had a lot of satisfaction from helping people kind of, pick paths to go and know how to pursue them and so on. Yeah. And so it's something where one tends to think about one's own kind of, what is it that I'm actually good at doing and so on. And I think the main thing that I sort of realized is that the thing that I can do is take these big complicated issues and sort of break them down into simple primitives and then build up practical systems based on those primitives. Yeah. So it's kind of like, one might think that building a computational language is a very different kind of activity from figuring out the fundamental theory of physics. But for me, it's not. For me, it's basically the same ultimate set of thought processes that happen in both cases.